All right, guys, 2.1, here's my take. We have to put each of these things into radian measure. You might remember, well, here, I'll show you guys. Boom. If we look at the unit circle, the way that radians are defined is that there's, well, it's essentially a rotation around the circle that's as big as a radius, So a bigger circle radius means a bigger radian, of course. But it turns out that regardless of the size of the circle, it's the number of radians that you can, or the number of radiuses that you can stretch out across the circle. If we were to just take this radius distance here, like from 0 to 1 here, and stretch it there, and then again and again, it turns out that it's a little bit over 3 times to get halfway across the circle, or in particular, it's pi number of times to get across the circle, or around half the circle, and then another pi number of these can stretch out to get 2 pi. Or to get all the way around. So 360 rotation is the same thing as 2 pi radians, or 180 degrees is the same thing as 1 pi worth of radians. And this is a good thing to consider. So as we're converting these things, notice that 180 degrees is the same number as, there's the same amount of rotation as pi number of radians. So if we were to convert these things, that's a good thing to keep in mind for a real quick take. This is what I would do. And there's a bunch of different ways, and you can shortcut this once you get used to it. If we have 310 degrees, we have, 310 degrees, I want to turn that to radians. Here's my take on these things. And this would be a good key to keep in mind no matter what. As we say degrees, if I compare that to 180, thinking degrees out of 180, that's the same thing as radians out of pi number of radians. Now we have an equal proportion here. This is indeed a true proportion. However many degrees we have out of 180 is the same number of radians we have out of pi of them. And you could do 360 compared to 2 pi, it's whatever, but these are just smaller numbers. And so then whenever you get this, no matter which way you're converting it, whether you're making degrees into radians or radians into degrees, this will always be helpful and true. And so then I can say, well, degrees, they're out of 180 for every pi number of radians. So I'll just kind of play that game. So in this case, we'll say 310 degrees out of 180 is equal to however many radians, I'll put R or something, out of pi of them. 310 compared to 180 is the same number as our radians compared to pi. And then you just kind of cross multiply like the olden days, and it'll be as good as gold. So we have 180 R equals 310 pi. And then we'll get the R by itself, and that's where you divide by 180. And we got ourselves a number of radians is 310 pi over 180. Or of course you can simplify that by doing like 31 over 18, 31 pi over 18, stuff like that. It's the same for all of these ones, just degrees out of 180 equals radians out of pi. And so let's see here, and it's the same thing with negatives here. Let me stop the annotation, boom, and then we'll scroll along, and we'll probably get rid of that stuff there I should have gotten rid of. Okay, so the next one, number 2, is the same thing as 290 degrees is to radians. So you do the same thing. Degrees out of 180 equals radians out of pi. And so it's just 290 out of 180 or whatever variation you have. Let's clear that up real quick. Okay, clear them, done. Now, if I have to do it backwards, it's still the same relationship. We still have degrees out of 180 equals radians out of pi, And so, we have a weird number of radians, so we'll just go with it, And so radians is 8/9 pi. Radians out of pi equals degrees out of 180. Feel free, if you happen to notice that the pi's cancel, you could do that right now, or else do it later. You could save that to the end if you like. But if you got pi over pi, there's no reason you couldn't do it now. But just say you didn't notice that. We could still just cross multiply as though they were still there. Then we got d times pi, or pi times d, equals 180 times 8 over 9 pi, and then you'll just divide the pi to get the d by itself for degrees, And so divide by pi, and the pi's end up canceling at the end if you didn't do it at the beginning. Now we got whatever 180 times 8 over 9 is. Maybe simplify that a little bit. It looks like 9 will go into 18 twice, so 9 into 180 should be a 20, and that'll be a 1. So we're looking like 20 times 8 over 1 times 1. That should be 160 degrees. Looks like we're looking at 160 degrees there. Kind of a nice whole number of them. And then, so you'll notice that when you have pi in there, given it looks like a weird number of radians, it ends up giving you nicer answers. And we may end up getting uglier answers here. And so let's hear about that. Okay, clear that up. Okay, 2.8 radians, 2 degrees. If I said, well, okay, degrees out of 180 is equal to radians out of pi, and then they give me a number of radians is 2.8. No big deal here, but you notice there's no extra pi to cancel it out, so pi will be left in the answer later, you know? And you times it and then divide that by and stuff. I'll just go ahead and full on cross multiply it, but you could just do this thing where if you like times it and then divide by the other one, that's fine. Anyway, pi times d equals 2.8 times 180, whatever the heck that is. And then you divide it by pi to get the old pi out of there. But boom. And then what I would do is if I were you, I would go ahead and either just times this stuff and then put it as some big old number over pi. They'll probably take that as the answer. Or else make sure that if you're going to put it in decimal form, just use the pi number in your calculator. Don't use 3.14. I wouldn't recommend. It rounds it off a little bit too early if you do it that way. And then, you know, you just times these, divide by pi button, and then shoot a big old string of decimals. They'll probably take it as long as you don't round it off before 4 decimal places. They don't really say where to round it to here. So that's why it might be safer just to put whatever 2.8 times 180 is, and then put that answer over the, you know, the little constant pi, and, you know, just as pi itself, instead of calculating it out. Anyway, that's my take on number 4. Let's see what we got elsewise. Oh, I'm still drawing. Okay. Woo-hoo. Big summer blowout. So we have, let's see, that was that one and that one. Number 5. Okay, going coterminal. We've done this with degrees, but here we are with radians, and it gets a little weird. So if I have 19 pi over 5 radians, remember, just like with degrees, when we're going coterminal on it, it's good for us to notice, well, okay, if I had, say we had something like, you know, it was like 1,000 degrees or something like that. Well, we were like, well, how many 360s is that? You know, that's 1 360, then 2 360s is 720. 3 360s is 1,080 though, so that would be too much. So this would end up being, you know, you'd be like, well, it's 2 360s, so that's chump change, and then, or it's to be forgotten. It doesn't help us. And then if 2 360s was 720 degrees, then we'll see how close we are to the 1,000, and that'll be the leftovers, and that's our coterminal angle. It works the same way with radians, and so if we have our unit circle with the radians all marked out for us, that'll be helpful for us. We have met 0 radians, pi over 6 radians, pi over 4 radians, a third of a pi radians, half of a pi radians, you know, on all these, you know, 2/3, 3/4, 5 out of 6, and then a full pi. You know, these are all fractions of pi because it's 1 pi to get halfway around. So this is at 30 degrees. Since a 30 is a 1/6 of 180, it would make sense that this is 1/6 of a pi as well, you know. And so then, you know, 60 degrees is a third of 180, you know. 60 times 3 makes 180. So this is a third of pi in radians, you know, to get to, I don't know why I would do that, but it's that angle. Anyway, as we were, got to find some coterminal angles. We'll go ahead and, oops. Yeah, there we go. We'll use that unit circle as needed, but here's this idea. We'll say, well, 19 pi over 5, I want to figure out how many times I spin around. So remember, every time I spin around in radians, it's not 360, it's 2 pi. So I got to figure out how many 2 pi's am I doing? There's 2 pi, 2 pi, 2 pi, 2 pi. You know, it's how many 2 pi's do we have? So then it's hard to know how many 2 pi's you have when you have a weird old fraction. So what I would do, and this is not, you know, you don't have to do this, but I would make it a mixed number and just see, well, how many pi's is this? 19/5? That's a weird number, you know? And so if I go 5 into 19, kind of, you know, 5 goes into 19, was that 3 times with 4 out of 5 left over. So this is 3 4/5 pi, you know, is another way to look at 19 pi over 5. 19/5 is the same thing as 3 4/5 pi. So then I'm looking at how many 2 pi's do I have in there? Well, what I have is, this is an odd number, but if I did, how many 2 pi's do I have? Well, I have 2 pi plus, and I don't have another 2 pi because 2 pi and 2 pi would be 4 pi, and I don't quite have 4. So it looks like I have just one set of 2 pi plus some extra. So it'd be like 2 pi, or I'll save the pi for later, but it's 2. And then with 3 4/5, that'd be 2 plus, and then the extra would be 1 4/5. Together, this makes 2 pi, and then the extra 1 4/5 makes the 3 4/5 number of pi's. all together. So this is how much pi radians I got, how many multiples of pi in radians I have. The first 2 pi is as good as done, because remember, that's just like doing a 360. And then that's, we've already gone around the circle. And now with the rest of the 1 4/5 pi, now that I got to figure out how big is that angle, because that'll be the next, what's left over in the next 360. And so 1 4/5 pi, that's a little bit weird to interpret. So I'll go ahead and make that back into an improper. 1 4/5, 5 times 1 plus 4 would be 5, 6, 7, 8, 9, right? So this is 9/5 pi left over after the first 2 pi. And so then I'll just look that up. Actually, I don't even have to look that up. That's not going to be on the unit circle, but I know that it's less than 2 pi. So I know this is what I have left over. So I'll just call it, well, it's 9/5 pi. And I don't really even have to put it in degrees or anything else nice. We'll just say, well, it's 9/5 pi. That's what's left over. Since that's less than 2 pi, that means I'm within the first 360 degrees. And the same thing is true with all of these. I would say, how many pi's do you have? And then see it, well, more than that, see how many sets of 2 pi do you have? And then whatever's left over is left over. That goes the same thing true with the negative. You just do the same thing, but just call it negative in the end. 3 goes into 7. 3 goes to 7, what is that, 2 times? And then there's 1/3, this is 2 1/3 pi. So there's a 2 pi right there, and the only thing left is 1/3. So then you'd say, well, this would be a negative answer, but it's 1/3 pi is what's left over after the first 2 pi. Whereas something like this, a big dog, it's going to have a lot more 2 pi's in it. And so here, I'll show you a big one real quick before we move on. 2 into 45. It goes into 44 evenly, right? So that's as a whole number or a mixed number, that's going to be 22 and then 1/2 left over. So this is 22 and a half. If I divide 45 by 2, here's the mixed number version, 22 and a half pi's. And so then how many 2 pi's do I got in that? Well, this is an even number of them. So I can do 2 plus 2 plus 2 plus 2 plus 2. It's essentially 11 of these 2's that it would take to add up to 22. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. There's 22 pi's. And the only thing that's left over is a half pi. So then we'll say, well, that's equivalent to doing, every time you do a 2 pi, remember, is a whole circle, a whole circle, a whole circle. And you're just doing all these whole circles. Essentially, this is like 11 laps around the circle. It's 11 laps around the circle. So we're just going to say, well, after the 11 laps, I only had a half of a pi left in me, which incidentally, if you look at it, half a pi, remember, is, well, a pi is a 180, 2 pi is 360. So a half a pi would be half of 180. So that's actually a 90-degree angle that's left over, incidentally. Not that you have to think about that every time. Okay, and that's how I would handle those ones. Clear all drawings. Okay, what else do we have here? Yeah, so then we're doing a little bit of right triangle trig with these things. Actually, it's unit circle trig, but whatever, it's always with the right triangle in mind. And so if they give me an angle like theta is 5 pi over 4, I have to find out these trig ratios. But once I get a feel for my radians, then that's not a big deal. And so what I would do is, really what I do is oftentimes I'll just kind of, because I've gotten so used to this over the years, and you guys probably will too if you work with this much, is you just kind of know what this looks like. Well, if this is a half of a pi, then a fourth of a pi is like a 45-degree angle. So this is a bunch of fourths of pi. So we'd be like 1/4, 2/4, 3/4, 4/4, 5/4 pi. I'm expecting it to be down there, 45 degrees past the 180. So whatever that is, 225 degrees would be the degree equivalent. This is 45 degrees past though. And so if I were to do like unit circle trig with it, or right triangle trig rather, with that, I know this is a 45-degree angle as a reference angle. And that means my over and my down are both the same amount. They're both radical 2 halves, And in this case, they're both negative because they're going to the left and down. That's how I would handle this. And then I would do my opposite and adjacent and hypotenuse is 1 and just run all my ratios that way. If you're not used to that stuff yet, though, don't worry. You don't have to have things like you have a perfect feel for things about what's a fourth of pi and this and that. Feel free to use the unit circle for what it's meant for. Get yourself a unit circle out, and then we'll just look for where in the world can I find 5/4 of a pi. And then after you do this a bunch, this is how I got used to it. Then you'll get used to it, and you say, well, 5/4. That's, I don't know. We'll find it. Here's 3 no, it's not even 3/4. That's 1/3. These are small fractions. 2/3. Here's 3/4. Here's 1. That's 4/4. 7 out of 6. That's weird. 5 out of 4 pi. That's it. 5 pi over 4. It's like a 45-degree angle. It's our 225. We're looking good. And now if they ask me for the sine and the cosine, I can do it right on the spot, because I know that, let's see here, this is the cosine and that's the sine, right? That's the x value and the y value is the cosine and the sine. They match. They're both negative, radical 2 over 2. And then I know that the hypotenuse is always 1, and so there. And now I can do any ratio we want, but we know that the cosine is radical 2/2. I also notice the adjacent is radical 2/2, and then the sine or the opposite is radical 2/2. They're both negative. So let's see what we can do about that. Boom, switch in. Okay, probably should get rid of that drawing. Okay. And then here we go. Now that we know what it is, the sine value was the down value. All right. All right, so the sine value was the down value. Here, we'll draw a little miniature of it. We have over here is the coordinates of the cosine and the sine, and they are both negative radical 2 over 2. So those will give you a couple of the answers right there, because they're asking for sine and cosine. They're both negative radical 2/2. That's easy enough. And then a tangent, remember, is the opposite over the adjacent. That is the opposite over the adjacent, also known as the sine over the cosine. And so it's that one over this one, or it's the y over the x, And so if we run that, that's negative radical 2/2 over negative radical 2/2, And so you could do all kinds of ways to simplify this, but any way you slice it, this is something over the same thing. So you might just call that a 1, because even if you don't know how to simplify it, it's something over itself, and so it's a 1. And then the secant, remember, is the upside down of cosine. So we can pull that from the cosine and just say, well, it'll be negative still, but now it's 2 over radical 2, And you could probably get away with leaving it like that, although at some point you'll be blessed by the habit of remembering how to rationalize denominators. So I'll go ahead and just remind you guys that right now, because you might need that skill in a couple of sections here. But it's okay. You can get away with the computer just saying negative 2 over radical 2 by switching the fraction upside down for cosine. That'll give you secant. Otherwise, remember how this goes, just as a tip, or else you can fast forward this part. We have, remember, to rationalize the denominator, so we don't have a square root on the bottom, and the fraction will be a lot more usable. What we can say is well, I'll just times by another radical 2 on the bottom. As long as I do it on the top, I can get away with that. And then I have the square root of 2 times 2 is the square root of 4. And then the top ends up being 2 radical 2. It's a negative on there, and it's 2 times the square root of 2. I don't know what to do with that. And we're pretty much done, except that 2 and 4, since they're both radicals, believe it or not, there's a property of radicals where you can simplify inside them, just like you would a regular 2 and a regular 4. So now we have negative 2 times, well, basically the square root of 1, which is going to be dumb, over the radical of 2. And so square root of 1 is 1. I'm going to not bother to times by 1. But now we have negative 2. Oh, whoops. I just simplified it right back to where it didn't need to be. Oh, yeah. Pretend that didn't happen. What I mean to say is it's over the square root of 4. And the square root of 4 is regular 2. So now we have negative 2 radical 2 over, and then the square root of 4 is just 2. And then you can leave it like that, or else simplify the fraction. What this ends up being is actually really nice. This is a negative of radical 2 over 1, or just negative square root of 2. So you can tell, of course, at times it's worth our time to, simplify these things out, because this is actually a nicer version in more ways than one than what we had before. So negative 2 over radical 2, or else just a negative of square root of 2 over 1 would be fine. All right. And then let's see here, clear that up. Okay. What else is there to know in this section? These things come from, on this one, it's sort of just looking at, it says t equals pi over 2, then what's the x and y value? This is just you saying, well, if we're looking at the angle pi over 2, what's the x and what's the y? So you just say, well, there's pi over 2, here's the x, here's the y, it's 0 and 1. You're just looking them up, getting used to knowing where these fractions are and stuff. What gets a little bit weird about it is if you get into negative angles, negative pi over 2, we can probably remember, well, if pi over 2 is 90, then negative pi over 2 would be a minus 90 degrees. So that's that 270, also known as negative pi over 2 is the same thing as 3/2 pi if you were to go the full way around. Either way, what's the x and what's the y? At negative pi over 2, it's negative 90 degrees. Here's the x and the y, it's 0 and negative 1, you know? And then weirder ones are, well, look at this one. Here's probably the weirdest, negative 3 pi over 4, negative 3/4 pi. That's not as easily found, you know, but what we could do is, again, look at what is regular 3/4 pi, you know? And so that's all the way over here. It's like a 45-degree angle in the middle, sort of, going up this way. So we're going to go, just like that one went 90 and another 45. This would go 90 and another 45, or in other words, 135 degrees going the wrong way. Now we have 3 pi over 4 would be that one, but negative 3 pi over 4 would be doing that same angle, but now it's downstairs. So 5 pi over 4 is the same thing as negative 3/4 pi if we run it negative. And now we have x value and y value, negative radical 2/2 for both. So I recommend for the negatives, just looking at a top version of the positive of it and then trying to copy it downstairs. And then let's see about question 8 here. Questions 8 and 9, we're doing more trig on radian values. I think that we did this a minute ago, this kind of thing, but let's just to be sure, let's do one real quick. So 5 pi over 3, I'll find the angle. Where's 5 pi over 3? 5 pi over 3, there's 5 pi out of 6, so I got to go further than this. You know, and we're just searching, you know, remember, these are 5/3, so that's like 1 pi and 2/3 pi. If you think of it as a mixed number, 5/3 is 1 and 2/3, so it's more than 1 pi, you know. Anyway, so 5/3 pi being improper like that, that's going to be on the bottom half of the circle because it's more than 1 whole pi. Here we are, but we found it. And then they want to know what's the sine, what's the cosine, what's this and that. Well, we know how to play the game here. You know, this is the sine is the y value, the cosine is the x value, and then anything else can come from those. And so here we go. On that last one, let's see the sine, because of the angle it was. Here, actually, before we annotate it, let's just get a feel for it. This angle is mostly down. It's like if we were to draw on that, just to get a feel for it, it's this angle right here. It's going more down than it is over. So it's a little bit over and a lot down. It's kind of more like a big 60-degree angle here, more of a 60 than a 30, you know, if you're to look at reference angle, meaning it's a lot down and a little bit over. So when we're thinking about y and x, what'll be easier for us to remember is that the sine value, the up and down part, that's the big one. It's radical 3/2. And the over part, that's the little one, so that's 1/2. So we'll see that in our mind as being, this is the radical 3/2 going downstairs, negative, of course. And this will be small going over because it's mostly a down angle, you know? And so that'll be a small amount, and this will be a big amount going down more. Okay, so that's our sine, that's our cosine, and then we'll just remember the rest. And so let's see here, we'll clear that all, and then back off of the annotation for a second, switch it, here we go. All right, 5 pi thirds, we can kind of picture again what that's like. Boom. That we noticed that our angle was like mostly down kind of thing, you know? And so if I go over a little bit and a lot down, I know that we're looking at the sine value is way downstairs. So that's negative radical 3/2, big number. And then that's over a small amount. So that's positive to the right, but it's 1/2 because it's small. There's our cosine and our sine. And so here we go. Sine value is negative radical 3/2. And then the cosine is 1/2, but it's to the right. So it's positive. Tangent is that one over this one. Sine over cosine. So it's radical 3/2 over 1/2. There's a negative in there somewhere, so don't forget that. Negative over a positive will be negative in the end. I'm just going to put the negative in the answer so I don't forget it. And then you'll notice they're both over 2. So you could do this thing where you flip times it and be like, well, to divide fractions, I times by the reciprocal, and it'll be 2 over 1, and then cancel the 2's. You know, that works real well. A lot of people, like at this point, since the bottoms always match, we'll just cancel them. We have radical 3 over 1, which is just radical 3, negative. And then secant is upside down of cosine again. And so you're playing that game where it's like, whatever, you know, it'll be, well, this is a very easy one, actually. I got a nice one. Hopefully you do too, right? And so this is upside down of 1/2 is just 2 over 1, or just 2. And then same thing with this one. I guess I'll go ahead and mention something about it though, real quick. Oops. Clear about the last problem on here. One thing I'm noticing about it, okay, is that it's a big, big angle. And so you'll notice that if you look around, you never find 13 out of 6, 11 out of 6 you'll find 2, you know, but this is too big for the circle. And so that means this has gone around one full circle and then it's gone more than that. And so let's remember, okay, if it's too big, if you can't find it in the circle, this might be bigger than 2 pi. And indeed, I think it is, because if you think 6 going into 13, 6 goes into 13 more than twice. It goes into 12 twice, right? And then so this would be 2 and some remainder. So this is 2 pi plus some extra. So if it's a big angle, let's find a small one that's coterminal so we can just reference that, you know? And so let's see here, if I annotate that, and we do, okay. Then we could say, well, 6 goes into 13 2 times with 1 left over. So this is 2 and 1/6 pi. 2 and 1/6 pi. So that means 2 pi plus an extra 1/6 of a pi. This is a whole way around the circle. So we can then restart our angle by saying, well, this is just like a full circle and then an extra 1/6 of a pi after that. So here we go. So this would be the same as our coterminal width. Same as just 1/6 pi or 1 pi over 6. So people just write it as pi over 6 a lot of the time. So as soon as I know that, I can look that up where I want it. And so here we go. Let's put that off. I know that it's pi over 6 now. Let's look here. Pi over 6 is this angle. It's 30 degrees because again, 30 degrees is 1/6 of the way to 180. So this is 1/6 of the way to pi at that same angle. Again, but whatever, just look it up until you get used to it. And so we have pi over 6. Here we go. There's a sine, there's a cosine, and then there was the rest of the story, you know? And so then you do your sine, your cosine, your tangent, just like we do. Hopefully this is a help to you guys.